should be seeing on the screen something which has 1 molar ethanoic acid, right? Need to remember is when you're working these questions, you want to write it in a format where you have the equation. For this equation, it's ethanoic acid reacting with ethanol. So for the acid, I'm going to put, okay, hold on. For the acid, I'm going to put RCOOH. And that reacts with ethanol. I'm just going to put the ratio sign to give water. I should go it over somewhere. Hold on. So RCOOH reacts with what ethanol to give water and an ester, RCOOR. Okay. So now what they're basically saying is this. 1 mole of ethanoic acid was allowed to react with 4 moles of ethanol. So you know what you're starting with. They tell you what you're starting with, right? The balanced equation is critical because if you don't know how to balance the equation, then you'll get the mole ratios wrong. All right. Now it says at equilibrium, the amount of ethanoic acid remaining is, this is low. The amount of ethanoic acid remaining is 0.07. So they tell you the amount of ethanoic acid remaining, but they don't tell you anything else. So when you're doing the questions, what you should have is your equation, then you have given, reacted, or formed, right? And then equilibrium. What's present at equilibrium? In this question, they gave you that you had 1 mole of ethanoic acid and 4 moles of ethanol, right? They said at equilibrium you had 0.07 moles of ethanoic acid. So the question now is, if you started out with 1 mole of ethanoic acid and you now have 0.07, how much reacted? You started out with 1 mole of ethanoic acid and now you have 0.07 moles. How much did you use throughout the day? You started out with 1, which means that you subtract the 0.07 from the 1, as you said. Okay?
Yes, sir.
So when you do that, now you get 0.93 moles. So it means that you would have 0.93 moles of ethanoic acid that reacted. That reacted. Hold on. I'm going to go to our thing there sheet, see if we can get a better view. Okay, so let's do this now. So remember what we had was our acid, RCOOH. It reacted with ethanol to produce water and an ester, RCOOR, right? So what I'm saying that you should do when you're given the question is write down the given, the reacted or formed, because reacted would be for the reactants. Some amount of the reactants would react, and then you would get products being formed. That's why I said reacted or formed, right? So this is a F. And then you have the thing at equilibrium. In this question, and you can divide it like this if you want to. In this question, you have 1 mole of that being given and 4 moles of alcohol. They say at equilibrium you have 0.07 moles of what is this now? 0.7 moles of acid. So it means that the amount that reacted would be 1 minus 0.07, which is 0.93. Okay. Now, since the mole ratio is 1 to 1 to 1, and I show you this is 1 mole of that reacts with 1 mole of that to give 1 mole of that to give 1 mole of that. Now, if this is the amount of moles of acid that reacted, it means that it must have reacted with the same number of moles of alcohol. So the amount of alcohol that reacted would be 0.093. So we write that there, 0.093. And because it is 1 to 1, still the amount of water which would be formed would be 0.93, not 0.093, 0.93. Okay, my point is not working enough. And then now the ester would be 0.93 as well. So now remember, this is the amount that reacted for the alcohol. But how much alcohol did you start out with? 4 moles. So if 0.93 reacted and you started out with 4 moles, then at equilibrium, what you're going to have would be 3.07 moles of alcohol. And because this amount was formed...
Sorry, can repeat why the rest of them is 0.93 moles as well?
Okay, so the acid, the mole ratio for the reaction is 1 to 1 to 1 to 1, which means that 1 mole of acid react with 1 mole of alcohol to give 1 mole of water and 1 mole of ester. So if I have 0.093 moles of acid reacting, it would react with 0.093 moles of alcohol to produce 0.093 mole. 0.93, I keep saying 0.093, 0.93 moles of water and 0.93 moles of ester. That's why all of these are 0.93. If it was like a 1, go ahead, sorry.
So what if it wasn't a 1-to-1 mole ratio?
Well, if it wasn't a 1-to-1, let's just say it was a 1-to-3, right? And this was 3. Let me change the color here. Red. Let's say this was 3 moles and this was 5 moles. And I'm using very random numbers here. And this was 4 moles, for example. Okay. And you know you had 0.93 moles of acid. Then 1 mole of acid will react with 4 moles of this. So you just multiply 4 by 0.93. Okay.
Okay.
And you'd multiply the 3 by 0.93 and the 5 by 0.93. All right.
Yes, sir.
In another situation where if this was like 2, the acid was 2 instead of 1, then what you would say, no, the ratio is 2 to 4. Let's just use that one. And we have 0.93 moles of this. So it would react with X. You then cross multiply. So it would be 4 times 0.93 divided by 2. That is what X would be equal to. Okay.
Okay.
So you could work that part out. All right, so good so far. Now it's saying here, no, so now we know the moles of acid, not acid, what do you call this now? The moles of alcohol, which is present at equilibrium. We also know the moles of water and ester that's present at equilibrium, 0.093, okay? 0.93. That's what present at equilibrium. Now, remember now, your equilibrium expression says that it is the product of the concentration of the products divided by the product of the concentration of the reactants. So what that means is that the equilibrium expression is Kc is equal to the concentration of water times the concentration of the ester divided by the concentration of the acid times the concentration of the alcohol, ROH. Okay, and this is at equilibrium. So all you need to do now, concentration of the acid, you put it in the equation. Here is the concentration of the alcohol, you put it in the equation. Here is the concentration of the water, put it in the equation. Same thing for that. Okay, and let's see if that's what they actually do when we go back to the question. Here we go. So this is what they have done. So they say, since the moles of that, and I explained all of that now, the expression now is Kc is equal to the concentration of the ester. Are you seeing what I'm showing you?
Yes, sir.
The concentration of the ester, why is this not changing? The concentration of the ester times the concentration of the water divided by the concentration of the acid times the concentration of the alcohol. And see there, they have 0.93 times 0.93. There you go. That's what we just wrote. Divided by 0.07 times 3.07. And this works out to be 4. So the equilibrium constant for this reaction, given these quantities, is 4. And now remember that the equilibrium constant is the same at a particular temperature. Okay, so it's not going to change at this temperature. All right. Note also, where is this thing now? Note also that it says down here, the concentration units cancel out as Kc has no units. The equilibrium constant has no unit, and the value of equilibrium constant is 4. All right. Let's see if we can go down to another question now. Partial pressure of a gas. Okay. In the reaction between hydrogen and iodine, so that's hydrogen plus iodine, you get hydrogen iodide. Notice now the mole ratio here is not 1:1, right? It's not 1:1. You know, you have a 1:1:2. Okay. And the equilibrium expression is HI, which is the product, squared from divided by the concentration of this times the concentration of that. Now, it says, since this is a reaction between gases, the concentration of the gas can be expressed as partial pressures. In other words, when you're looking at solution, call it concentration because it's a liquid. But when you start talking about gases, you can talk about partial pressure of the gas. So if I have a balloon with 3 gases inside, all 3 gases are going to be contributing to the pressure or to the size of the balloon, right? Because all those gases will be bouncing on the sides of the container. How much pressure each gas contributes to the thing is now called the partial pressure. Sorry, it's called the partial pressure. Okay. So we proceed. So you can now write an expression where it is Kp instead of Kc. Notice the notation. This is equilibrium constant for liquids, and this is now partial pressure equilibrium constant. You can still, it's the same expression, it's just that you're now using partial pressures. So this is a partial pressure. The partial pressure of hydrogen iodide squared divided by the partial pressure of hydrogen times the partial pressure of iodine. Okay, now it says Kp is the equilibrium constant in terms of partial pressures. So now here's a question. 1 mole of hydrogen and 1 mole of iodine are mixed and allowed to reach equilibrium at 300 K and the pressure of 1 atmosphere. The amount of hydrogen iodide present at equilibrium is 1.5 moles. Calculate the equilibrium constant Kp at 300 K. So let us look at that now. I'm not even going to look at the thing right down there because I don't like how they do it. So just remember the numbers. 1 mole of hydrogen, right? This is rough. 1 mole of hydrogen and 1 mole of iodine reacted. And it says at equilibrium, you had 1.5 moles of hydrogen iodide. All right, so let us remember those numbers. We go over here now. We clear all drawings. So first thing you want to write the equation. So the equation was H2 plus I2 produces HI, and there's a 2 there. Okay. Then now you want to say write down given. Given, that's the given. Okay, and I think it was 1 mole of this. Reacted or formed now. And then you have equilibrium. I should just write G-E-R. Okay, so now let's look at it. I'm just trying to separate the different aspects of the thing. Okay, so it said though at equilibrium, how much do you have of hydrogen iodide? 1.5 moles. Okay, now what we want to find out is this. We want to find out, right? The equilibrium amounts. That's what we want to find out. Now the question is this, right? If I started out with 1 mole of hydrogen iodide and 1 mole of iodine, and I ended up with 1.5 moles of hydrogen iodide, how much hydrogen and how much iodine would have reacted to give that? That's the question. Okay, and that's what we're trying to figure out now. So I don't this. If 1.5 moles of hydrogen iodide is at equilibrium, it means that 1.5 moles of hydrogen iodide must have been formed. Do you see formed? It can't be present at equilibrium if it's not formed. So now if you look back at the mole ratio in the equation, I'm just going to change the color here. 1 mole of this reacts with 1 mole of this to give 2 moles of this over there. So if 1 mole of that reacts with 1 mole of that to give 2 moles of this, which is the same number, 1 and 1, what you need to now find is how many moles of hydrogen would react to give 1.5 moles. So what you're going to do now, you're going to say 1 to, okay, this is not 1, Jesus, to 2, Come on. Therefore, x to 1.5, because you're trying to find out how much would produce 1.5. Okay. 1 to 2 came from the equation. That's theoretical. In practice, we actually have 1.5 instead of the 2. So how many moles of hydrogen would give that? We now cross multiply. X is equal to 1.5 times 1 divided by 2. What's 1.5 times 1 divided by 2? Where is it? 5. Excellent. So we now know that 0.75 0.75 as well must have reacted to produce that. How do we know that? Because we know that 1 mole up here produces 2 moles. But instead of 2 moles, we got 1.5. So how much would produce that? And we'd have to cross multiply for that. We'd have to do this little expression that we did here to get that. When we did that, we got X. So notice now, it says here that 0.75 moles of hydrogen reacted and 0.75 moles of iodine reacted, and you ended up with 1.5 moles of hydrogen iodide. Do you see that? If you started out with 1 mole of hydrogen and 1 mole of iodine and 0.75 moles of both reacted, how much do you have at equilibrium? We know the values at equilibrium, 0.25, and this one is 0.25. So now that we know the numbers at equilibrium, we can now calculate Kp. So I'm going to clear all drawings. So what our Kp was equal to the concentration of Hi squared, P, not concentration, P, divided by pH 2 times P8 I2, Pi2. And at equilibrium, we had 1.5 squared divided by 0.25 squared. So you can work that out now. Work that out. What is 1.5 squared divided by 2.5 squared? And that works out to be 36. I'm sure if you had your calculator, you get the correct answer. But okay, 36. It says phosphorus pentachloride dissociates at high temperatures. There you go. And notice these are all gases, so we're going to be looking at partial pressures again. It says the system reaches equilibrium at a certain temperature when 39% of a sample of PCl5, which is phosphorus pentachloride, has dissociated. 39% has dissociated. Why are they doing this? This is evil. The total equilibrium pressure is 2 atmospheres. Calculate the value of the equilibrium constant. So there you go. They do it the right way this time. So let us look at it first. They write the equilibrium expression, right? Kp is equal to PCl3 times PCl2 divided by PCl5. Then now it says since PCl5 dissociates like this, notice they're given the equation first, right? The original amount of PCl, why did they put 1? I'm not sure why they put 1 because 1 wasn't given. But anyway, we can start with 1. It could be 100, it could be 1. It doesn't matter. All right, so the original amount of PCl5 is 1 mole. And at the beginning, you notice you don't have any PCl3 or Cl2. So this is why these numbers are 0 and 0, right? At the start of the reaction, you don't have any product. You just have the reactant. Well, no, what they're saying is at the equilibrium, notice the equilibrium amount, you have 0.61. Why did they say 0.61? Because a system reaches equilibrium at a certain temperature when 39% of a sample of phosphorus pentachloride has dissociated. Okay, so what they're basically saying is, if I started out with 100 molecules of potassium pentachloride, I keep saying potassium, phosphorus pentachloride, right? When it reaches equilibrium, 39% would have reacted, or 39% would have been used up. If 39% has been used up out of 100, how much is left back? So if I started out with one thing, okay, and I've used 39% of that one, it's going to be 39 divided by 100 times 1, right? 39 divided by 100 times 1. it is basically 39 divided by 100, right?
Yes, sir.
And 39 divided by 100, we move the decimal point 2 places to the left. So we end up with 0.39. Okay, so 39% of 1 is 0.39. They are saying that you use 39% of 1. So how much do you have left? You're then going to say, okay, I started out with 1. I use 39% of it, which is 0.39. So it's 1 minus 0.39, which works out to be 0.61. Okay, and that is where the 0.61 comes from. All right. Now we want to identify where the 39 came from. Okay, so we know that 39% of the phosphorus pentachloride was used, right? And you started out with 1 mole of it, which works out to be 0.39. So you basically use 0.39 of the 1. Now, if 0.39 moles decompose, since it's a 1:1:1 ratio, it means that you would produce 0.39 moles of phosphorus trichloride and 0.39 moles of chlorine, because it's a 1:1:1 ratio. Okay, numbers over here now. At equilibrium, because you now have 0.61 of that and 0.39 of this and 0.39 of this, to get the total, all they did was simply add up all 3 numbers, okay, to get the total, which is what they have over here. Now that we have the equilibrium amounts, what are we going to do with these numbers now? So it's going to be 0.39 times 0.39 divided by 0.61. And then that now becomes pretty straightforward. You can then see your answer down here. Okay, see, there you go.